In this lesson, we're going to learn about logarithmic functions. Now, a logarithmic function is written y equals log base a of x. And that is true if and only if x equals a raised to the y power. So our output, y, is an exponent. So when you have a log function, that output is an exponent. And I'm going to write here how we say this. Log base a of x. So y equals log base a of x. Now this is called log form. This is called log form. Now, just because it's a log function doesn't mean it has to be written in log form. We can write a logarithmic function in exponential form. Now, this is also an exponential form, but it is also a log function. The reason why we know it's a log function is because, once again, the output of y is the exponent. When the output is your exponent, that is when you have a log function. So both of these are log functions, but this one on the right is exponent form, not an exponential function, exponent form of a log function, which is very helpful when we're graphing. And this one on the right is log form, logarithmic form of a log function. So both of these are log functions. Now we can write a log function, log, and then we have a base, and that's a subscript, and then we have what we call an argument. So of the argument is equal to the exponent. So log, and then the base is a subscript, and then of the argument equals the exponent. This right here is log form of a logarithmic function. Log form of a logarithmic function. I can also write this in exponential form. Base raised to an exponent but that exponent has to be your output. So that exponent has to be y, right? Is equal to the argument. So you can write it in your exponential form. Now there are two important logarithms. There is a common logarithm. That's the most common logarithm. It's base 10. That is what we call a common logarithm. So this is called the common logarithm. And then we have what's also very familiar is the natural logarithm. So we have a common logarithm and a natural logarithm. The common is a base 10. So base 10 is a common logarithm, and a base e is your natural logarithm. So if you see log base 10, you can just write log log, and it's assumed that the base is 10. If you see log base e, we rewrite that ln for not natural logarithm. So ln, probably logarithm natural, ln. Logarithm comes first because it's most important, and then the natural that describes it, that's going to come second. In other languages, that's what they do. They put the adjectives at the end, and that's my assumption is where that comes from. Now, the domain of a log function in the form above is when x is greater than 0. So your argument, more specifically, your argument must be greater than 0. So it has to be positive. And then one last thing that we want to do is we want to make sure that you know how to write these. So here's like a little writing tablet type thing. So if we were writing a logarithm, we write log, and then you'd have the base as a subscript. So your base would be a subscript, and then you would have your argument, which is on the same line. Now sometimes I put the logarithm or the argument in parentheses, and then equals y. So you can see that, let me do it without the parentheses here so that you can see that. I know this seems silly that we're learning how to write this, but your base is a subscript, but the argument is no longer a subscript. And then your exponent right here, y is your exponent, right? So that's your exponent, and your exponent can be any real number. Any real number. Okay, I think I covered everything. The base has to be greater than 0, but not equal to 1. So we've got a restriction. Let's highlight our restrictions, maybe bubble them in purple. So that's a restriction right there. The argument has to be greater than 0, and your base has to be greater than 0, but not equal to 1. Okay, so let's practice, because that's how we're going to learn how to do this. We've got a base of 4. We have an exponent of 2. And then 16 is going to be the argument. And we want to write this as a logarithm. So log base argument equals the exponent. And now we're just going to plug all of those values in. We've got a base of 4. We have an argument of 16. And we have an exponent of 2. So 16 equals 4 squared becomes log base 4 of 16 equals 2. And you will get very used to being able to identify that this is correct by saying 4 raised to the second power. Let's take that straight tool off. 4 raised to the second power is indeed 16. So I just do a quick check, and it works. I love that color. Color really helps, hopefully helps you see what's going on. So here we have a to the third power is equal to 2.1. So we have log base a of 2.1 equals the exponent of 3. And that's, these two things are equivalent. A cubed equals 2.1 is the same as log base a of 2.1 equals 3. Same thing. It's a true story. Now we're going to go backwards. We're given our logarithm and we want to write as an exponent. So we have log base 3 of 1/9 equals -2. So 3 is our base raised to an exponent of -2 is equal to 1/9. And that is exponential form. Exponential form. So we've got our base. We've got our exponent. And our 1/9 is the argument. And for a logarithm, your expression is equal to the argument. So let's look at when we have a natural log. Let's write as an exponent. We have natural log of x. The natural log of x is equal to 4. Remember that the natural log, ln, is the same thing as, is equal to, the same thing as log base e. So when I first start becoming acquainted with logarithms, I'll rewrite this so that I can see the base. Log base e of x is equal to 4. Now I can very easily write this as an exponent by saying e raised to the 4th power equals my argument of x. And that's rewritten. So that is the same as the natural log of x is equal to 4, the exponent. Now, once we get used to writing logarithms in exponential form, it's not too difficult to evaluate without a calculator. So here we have log base 8 of 8. So I'm going to rewrite this. Log base 8 of 8. And I need to evaluate this. What is that equal to? Well, we ask ourselves, 8 raised to what power? 8 raised to what power is equal to 8? Well, the answer to that is 1. 8 raised to the 1st power is equal to 8. So log base 8 of 8 is 1. 8 to the 1st power is equal to 8. Log base 8 of 8. Sometimes we might say x. We don't know what that is. So sometimes we put an x there. 8 raised to what power is equal to 8? Well, 8 is the same thing as 8 to the 1st power. So 8 to the x equals 8 to the 1st. That means that x equals 1. So log base 8 of 8 is equal to 1. Lots of different ways that you can approach this. It all depends on the level of difficulty. Sometimes I put equals x, and sometimes I don't need to. Sometimes I can just look at the problem and figure it out. For instance, let's do the next one. Log base 1/3 of 9 is equal to what number? So 1/3 raised to what power? 1/3 raised to what power is equal to 1/3 raised to what power is equal to 9? Well, you might be able to do this in your head if you know your exponents. You might see that, oh, I need to flip that 1/3 so that it can be a 3 over 1. But then I'm going to have a negative x, right? So what would x have to be? Well, x would have to raise some negative number. I'm not going to put negative x. I'm going to put some negative number. I could put negative x. Negative x. 3 raised to the opposite of negative 2, right? So that might be a little confusing. But if you know your exponents, it's not confusing at all, because you go back to the original and you say 1/3. Well, I know 3 squared is 9, but it can't be 2 because 1/3 times 1/3 is 1/9. I need to flip it to be a 9, so that would be negative 2. So 1/3 raised to the negative 2 power is equal to 9. And what we're going to do later on is we're going to do something like this. 1/3 raised to the x power is equal to 3 squared. And I've got, this was kind of what I was going for in that other problem, and I was like, well, maybe that's going to confuse you a little bit. You get the same base, and then negative x equals 2, so x equals negative 2. And that's exactly what we got right there, negative 2. We have log base 5 of the cubed root of 25. So log base 5 of the cubed root of 25 is log base 5 of 25 raised to the 1/3 power. So that's going to be log base 5 of 25 raised to the 1/3 power. And this is a problem where I'm going to put equals x, right? So the reason I'm going to put equals x is because it's going to help me say, okay, well, 5 to the x is equal to 25 to the 1/3 power. And 25 is the same thing as 5 squared. And then 2 times 1/3, power to a power rule, is 2/3. So x must equal 2/3. So what does this equal? This equals x, and x is 2/3. So log base 5 of the cubed root of 25 is equal to 2/3. So again, it all depends on your level of understanding, your math facts, and also not just your level of understanding, but your level of problem, the level of difficulty of the problem. So number 7 is much more difficult than number 5. So maybe number 5 you could do in your head, but number 7 you need a little bit of assistance. Set it equal to x. Eventually with practice, you may be able to just rewrite and get this answer of 2/3. But quite honestly, that would be, just me looking at it, would even be a little difficult for me. So don't put too much pressure on yourself. Go ahead and set it equal to x if you find that that's helpful. Okay, we're going to talk about the domain of log functions. So remember earlier we said the domain of a log function. The domain, that's your inputs, and x is your input, right? That's your input right there. So if x is your input, the domain says that the argument has to be greater than 0. So that means our domain here is going to be x minus 1 is greater than 0. So you set that argument, you set your argument greater than 0, not just the x value. What inputs am I allowed to put in that are going to give me an argument that's greater than 0? So x is greater than 1, we add 1 to both sides. So my domain for this function is 1 to infinity. Same is true on the next one. We have h of x equals 8 plus 5 times the logarithm of 2x plus 3. Our argument is 2x plus 3. So it's not just x that has to be positive, because maybe x can be negative. It all depends on the argument. It's the argument that has to be greater than 0. So you set that argument greater than 0, subtract 3, divide by 2, and we get x is greater than negative 3/2. This is a great example because you can have some negative values, but the argument is going to remain positive. So it's not about just x, it's about the entire argument. So make sure that you're setting that entire argument greater than 0, not equal to 0. So these are open intervals. Open intervals have the parentheses. Okay, let's move to our calculator because we are going to have to do some work with a calculator. We want to evaluate the natural log of 5 divided by 3. This can be rewritten 1/3 times the natural log of 5. So dividing by 3 is the same thing as multiplying by 1/3. Number 11 is a little bit different because the argument is 5/3. So I like to write in handwriting, I like to put my argument in parentheses because this entire argument, this is different. This is the natural log of 1 2/3, which is what the natural log of 1.6 repeating, which is very different than the natural log of 5. We're not going to put 1 2/3 in our calculator. We're not going to put 1.6 repeating in our calculator. We're going to put this into our calculator. For number 10, we're going to put 1/3 times the natural log of 5 into our calculator. And for number 12, we've got log of 15, that's log base 10 of 15, plus log base 10 of 20. That entire numerator is going to get divided by the entire denominator. So let's move over to our camera, turn our calculator on, and there it is, camera. So we have the natural log of 5 divided by 3. Now if you have a fancy calculator, you can just hit natural log of 5 in the numerator and then 3 in the denominator, and it looks just like the problem does on the paper. Or you can 1 divided by 3 times the natural log of 5, and you get the same answer. If you have a calculator where you have to do one piece at a time, you hit the natural log of 5, enter, and then divide that entire value by 3. And we still get 0.536. 0.536. So what I do is if I don't have a graphing calculator handy, I will find the natural log of 5 and then divide that result by 3, and that gives me 0.536. Okay, let's look at the natural log of 5/3. So the natural log of 5/3 would be the natural log, and then in parentheses, I put 5 divided by 3. Now my calculator's probably going to change that to a fraction. Maybe not. Okay, yours might. It might make that look like a fraction. The natural log, and then notice how I put in parentheses the entire argument, 5 divided by 3, and I get a different value, 0.511. 0.511. So this one is approximately 0.511. Now number 12, if you have a fancy calculator, or if you're good with even putting parentheses and your division bar and all that, you can, and I'll do it that way first. Log base 10 is just log. So log of 15 plus log of 20. I'm going to divide that by all of the denominator. Natural log of 15 plus natural log of 20. And I get that value right there. If I put this into a fraction, the log of 15 plus the log of 20 over the natural log of 15 plus the natural log of 20, and I get the same value. And our answer there is 0.434. Now, for those of you who don't have a graphing calculator, you should consider getting one if you're going to go to calculus. That would be a helpful thing for you to have. But this is what you can put into your calculator and get it right every time. So log of 15 plus log of 20, and then divide that by natural log of 15 plus the natural log of 20. And I personally usually put parentheses around my argument. You've heard me say that already now a couple of times. Once we start getting a little bit more complicated with the algebra, it does help. It does make a difference. It helps you see some things that hopefully are helpful for you to see. Okay, let's move along to graphing. And I am going to use my graphing calculator again to show you some graphing, but let's move on to graphing. Actually, I'm going to move on to graphing in another video. This way I can use my calculator a little bit more, because these videos, when I use that camera, it soaks up a lot of data. So I'm going to come back in the next video, and we're going to talk about the domain, the range, the asymptotes of our functions. You can see we've got an exponential function and we have a logarithmic function. So we'll be talking about that in the next